And Judy Peterson's back up to introduce the next set. If you're going to ask a question from the floor, you must use the microphone because we are recording the questions, and while the audience may hear you, the recorder cannot. So please remember that and just use the microphone, okay? Although in the future, we're going to try to work off our card session. So this next, after lunch, we're going to break for lunch. After lunch, you're going to come back and you're going to go to 1 of 5 rooms. And because all of the people that we have in each of these 5 rooms are doing something a little bit different, we thought we'd take a few minutes and let them give you a quick overview of what they're going to be doing for an hour. So it'll be a smaller group of people working with the scientists who are doing these models, or working with tools, or working with ways of communicating to the public that I think you probably haven't necessarily had experience with, and I think it'll be something that'll be very valuable. So I'm going to just let them come up here very quickly, and I'll call them up one at a time, and have them give you a quick overview. Bob Beardsley is from the Woods Hole Oceanographic Institution, and his colleague Changsheng Chen is from UMASS Dartmouth. And do I have to read this? Are you going to summarize it for us? It's sort of like Dr. Strangelover, how I learned to love the bomb. They're going to talk about their 3-dimensional model, hopefully in a way that we all understand it.
That'll be better than I understand it. Well, I want to thank Kirk for giving a great introduction to part of what we're going to talk about today. In terms, he introduced a lot of concepts. The things in the New England, not just hurricanes, but nor'easters and storms like that. I want to mention one thing about nor'easters is that they travel slowly compared to hurricanes, and they can stall, and so you can have a combination of near hurricane strength winds over a large fetch for long periods of time. The waves can get huge. And we found in our studies, for example, at Scituate, where we've been doing inundation studies, that wave current interaction can make the storm surge higher. So in certain places, that's really critical, and we'll get to it. FVCOM, that stands for the Finite-Volume Coastal Ocean Model, or Coastal Community Model. Community Ocean Model. And what we're going to talk about is that this is a relatively new model, dynamical model, to forecast coastal inundation driven by the regional and to local scale changes in the atmosphere and ocean forcing due to climate change. Again, I just want to repeat something that Kurt said. This also includes precipitation, the floods, waters coming down to the coast, and it also includes, although not mentioned yet, is isostatic rebound of the land so that the water is getting deeper. This is not a big deal in some places, but it is a big deal as you go further north from Boston and into the Gulf of Maine, and particularly further north. And some of you may know that the Gulf of Maine and the Bay of Fundy is a natural resonance system for the semidiurnal tides. And in fact, recent studies have shown that this change over the next 50 years is going to lead to increased tidal amplitude and increased high tides. So the timing of when a storm comes through, a nor'easter comes through, or a hurricane comes through, really need to get maximum inundation is you need the combination of waves, you need the combination of winds, you need a combination of and you want it to happen at high tide. Okay, so what do I do here? I press a button. Okay, so some of this is repeat. This is where the tide stations are in New England. You'll notice that there's large spots where there's no tide gauges. National Weather Service has been putting in some. They helped put in one here in Scituate. There's another one in Hampton now, and hopefully there'll be more up here. Anyway, this shows for both for Boston and for New York. It's already been made that sea level at the tide stations, or mean sea level has been going up, again, at a higher rate than at other places. This ends up, I think, being about, just from this alone, represents something like, I think it's like almost a quarter of a meter in 100 years. Now, this is a little complicated, but I want to talk to you about something called the Northeast Coastal Ocean Forecast System, NECOFS. This was developed primarily by funding from the Northeastern Regional Association of Coastal Ocean and Ocean Systems, NECOFS. And it's centered around FVCOM as the core ocean model. It's driven, and I should say that this is a forecast system. So this was developed actually to provide every day a 3-day forecast of surface weather, surface forcing, surface elevation, and temperature and salinity. Here are the products put down here. But basically, it was designed to be a forecast. It was started in about 2007 with funding from NIRCUS. And one of the objectives of this was to provide what they call end-to-end inundation forecasting. In other words, you start with an ocean model and you end up forecasting inundation in some local place. So that was one of the objectives, besides just providing a forecast that other people can use, like the National Weather Service and so forth. So we have our atmospheric forcing from the national model that goes into a local model, which is a regional model. By regional, I mean the whole Northeast, including parts of Canada. That provides the surface stresses and forcing for the regional ocean model. That provides forcing also for a coastal model, which is Sea Grant has been very helpful in providing funding for that. And the resolution here is down to 10 meters. And then recently, in the last few years, we have developed storm surge models, just like the one that Kurt showed you, for Scituate, Boston, and Hampton. And Scituate and Hampton were picked as places to demonstrate this end-to-end capability by the National Weather Service in Taunton. And Boston was actually encouraged by and funded by Chris. And so I want to thank MIT Sea Grant for being a real source of support and encouragement. And one of the things that actually came with the most recent grant from Chris was to look at the role of climate change. Can we use this as another tool for looking at climate change? Okay. So again, this is a dynamical model, ocean model. It's driven by boundary conditions are driven by a global FVCOM model, which will show local river discharge and so forth. We have a surface wave model called SWAVE, which is used, also driven by the local weather model. We take in some data that we can as a simulation, and I think that's basically what I want to show here. Okay, so I'm going to show you some of the grids so you see. Okay, one more slide. Okay, some of the grids. I'll go very fast. So this just shows you the nesting. Global drives the boundary conditions for the regional, Northeast regional. You can see Boston right here. This is the Mass Coastal, Boston here. And then these are the high resolution grids for Scituate, Boston Harbor, and Hampton, and actually Saco. I think that's one more. So this afternoon, we'll give some examples of how this is being used to look at the impact of climate change and so forth. We'll do some more work on the historical tide gauge. We'll give you a case study of Hurricane Bob, which shows, again, the role of how these dynamical models and how you actually, this is a hindcast where you can actually compare. Somebody talked about calibration. You definitely have to do it, even though it's in the past. If you believe this is a dynamical model, if you force it with the right conditions that represent the past and it works, you have confidence that if you run it with a future condition, the dynamics will take care of itself. The only uncertainty is what the future condition is, and that's why these ensemble approaches and Monte Carlo approaches work for the future, for the far future. Okay, and then we'll just give you some descriptions of what we're doing in the nor'easters, because again, as Kurt said, they're the major storms that we have to worry about and face. Okay.
Great, thank you.
All right. I'll leave these here.
Yes.
And somebody might want to use this.
Yes, I think so. Thank you.
Yeah, thank you.
I think that whoever goes into that session will really enjoy hearing about this model, and it's very exciting because of the potential and certainly because of the three-dimensional component of it.